Hi, can you hear me? Okay, good, you can hear me. Right, so welcome to the closing keynote. Now it works. I hope you've had a nice day so far. I'm going to try not to ruin it. So you might be asking yourself, who am I? And you'd be right. My name is Katharina. I'm a software engineer at Ferrous Systems, one of the sponsors of the conference. I'm based in Berlin. We do all sorts of Rust consultancy. I spend a lot of time doing embedded work, but over the last few months I've been doing a lot of networking as well, and async is sort of a big part of that. If you want to live complain at me, you can do that. I read my Twitter pretty actively, although not right now, obviously. But also, if you have questions afterwards and you don't meet me, or you're shy or whatever, send me an email, and I'm usually pretty quick to respond to questions and stuff. I also make some pretty atrocious puns, and normally on conferences I put that in as a warning for the slides. In the Rust community, it's more of a badge of pride, I guess. But also a warning, the slides are terrible, so yeah. Right, so when I initially pitched this talk, or the idea for this talk, I thought it would get 30 minutes. And you can do an async talk in 30 minutes. And that was the talk title. And I wanted to make like a Star Wars-inspired logo, but I didn't have the time. But ultimately, I was given more time, and I think this is good because I ended up wanting to make this talk, which is slightly different. It's still going to have async in it, but please keep in mind that I'm going to go on about something in the beginning that doesn't have anything to do with networking, but does it? So I have a point with all of this. Just don't be confused, please, or at least we can be confused together. So I want to make a statement, which hopefully isn't too controversial, which is that Rust is successful. And I see some people nodding and some people looking at me with this question in their head, which, yeah, you're right. How do you define success? And I'm going to try to actually do that and not just put the question into the room and then never go back to it. So right, Rust is a pretty young language. We've heard this from a few talks today, yet like the language only really started in 2010. I actually don't know when it was announced. I think a little later than that. But like it's been only stable since 2015. And that also means, so like the language is 3 years old, but that also means that the Rust communities are pretty young. Obviously, some people have worked on Rust before it was stabilized. Some people are probably sitting in this room. I didn't. And I know like most people, the vast majority of people that I know who develop in Rust today didn't work with it before 2015. They picked it up with the stability of the language. Yet that hasn't stopped anyone from actually making some really cool stuff and building quite impressive ecosystems, really unlike anything that we've ever seen in other languages as well. And like the landscape is changing as well. You have lots of companies now that are using Rust and adopting it. Just look at the sponsors outside, and for every sponsor here, there's like 10 more companies that are dabbling with Rust that don't sponsor conferences, but they still use it. And finding Rust jobs is incredibly easy as well these days. I actually had an interesting encounter in a hackerspace a few weeks ago where I was explaining something to someone about like the borrow mechanism in Rust, and this random person I had never met was like, hey, you know Rust, do you want a job? We work with Rust, and how wouldn't that be better than your day job? And it was like, about that. So, it's pretty cool. And I think all of these phenomenons can be boiled down to momentum. Not that type of momentum, but social momentum, and also development momentum. Development momentum in the sense of, Rust gets a new stable release every 6 weeks. That's a pretty fast cycle when it comes to a language. It takes not that much time between you writing a PR to the standard library and it being in the standard library and everyone using your code. The contribution pipeline in general is incredibly short. And the processes to involve yourself in these processes is incredibly open. So about success, I want to step back a little and look at this quote from the Rust book. I don't think this was in the original version of the first iteration of the book. At least I didn't see it. The first time I saw this quote was when I got my copy of the Rust book as a dead tree. And I opened it up and I saw this foreword, and I was kind of surprised, or I was delighted by it, because I saw myself in this a lot. And I also saw a lot of people I know who write Rust these days in this quote. It echoes a sentiment that we've heard a few times today about empowerment of developers, empowerment to write new applications, to do systems programming, to do all sorts of things. And so, it's a pretty big theme in the Rust community, and it made me ask the question, is the Rust community unique? Well, no, it isn't. I don't think it is. I could think of a few different open source projects that have similar mechanics, and they're just as open, and they have an RFC process, and collaboration is quick and whatever. What is unique, though, about Rust as a language is that the tooling supports developers in a way that other language ecosystems don't. So what that means is that people have the means more to write things outside of their original scope than in other languages. And you can see this with the list of places Rust has gone to. People write networking services. People do embedded work. Ashley this morning talked about WASM and writing browser front-end components in Rust. You can write all sorts of general applications, games. There's people writing software for space, which is pretty cool. And so I think that is a sign of a community of empowered developers who became that way because of their tooling. So people writing things supported by the tools that they're writing them with. And in my opinion, this momentum is the success of Rust. So looking at what kind of people are being brought into what domains and what type of projects they then write is the momentum of the language, and I think that makes Rust successful. It's people who are curious. We had this curiosity in Pascal's talk about just looking at different concepts and exploring ideas that were present in other languages, ecosystems, frameworks, whatever, and bringing them to Rust and adapting them and being supported by the tools and the community as well, who are then encouraged to build really cool stuff. This isn't easy, and this isn't perfect. The Rust community does definitely have problems. If you haven't seen it already, I would really recommend the opening keynote at RustConf, which talks about exactly these problems, scaling up the decision process, bringing in new people, and as the Rust project and the Rust community becomes larger, still making it possible for people to contribute in the same sense that then, in the same sense as they are contributing now or have been in the past, to keep that pipeline open. Right. So far so good. I want to talk about Rust 2018 a little. Who here in this room doesn't know what Rust 2018 is at all? And if you're watching this online, please leave a 0 and a / comment. I want to read them afterwards. OK, so basically everyone here knows what Rust 2018 is. That's nice, because it just came out. If you're unfamiliar with some of the scope of the changes, it's accumulation of changes since 2015. Some of them are breaking changes, and we're going to look at that in a second. And the focus of this edition was on ergonomics and productivity, whereas in 2015 it was about stability. Now it's about ergonomics. The way that breaking changes are handled are with an addition flag. 2015, there in the addition field is the default, which means that all of your code is still going to compile. You're not going to have any breakages. And if you want to opt into breaking changes, then you just set that to 2018. But that wasn't all that the edition was. There was a bunch of technical changes that I don't really care about right now. The thing that I care about was the working groups. So in the beginning of the year, there was an announcement of working groups, 4 of them, command line applications, embedded, WASM, and networking. And the idea behind these groups from the announcement post, a quote, the goal of these groups is to focus on the end-to-end user experience of using Rust in each domain. So far, so good. The governance of these groups was in line with the rest of the governance of the rest of the community. So like they had leaders assigned to them at the beginning that sort of kicked off a group meeting and sort of helped organize. And then people joined through collaboration. And really looking into the groups now, 8 months after they've been announced and they started, they became less hierarchical the more time went on and the sort of more people joined, the less hierarchical the structures became. And this was meant as a low barrier to entry for newcomers. And in fact, that's how I joined the Rust community. I've only been writing Rust for about over a year now, and I wasn't active in the community a year ago. So like, that's how people come on board. I was gonna do like a whole section about some changes, but it was way too long, and like there's so much stuff that was done. I encourage you to read the new website. If you go onto the main page, scroll down a little, there's this section where each working group sort of has a highlight of stuff that was done. So, yeah, this is a talk about async development, if you hadn't noticed. So the announcement post of the networking working group, which is a bit of a mouthful, was focusing on the end-to-end experience for both sync and async networking code, which begs to ask the question, what is Async IO? And that's what I'm going to go into now. So Async IO is fundamentally about using available resources the most efficiently as possible. We live in a world where we have computers that have a lot of cores and can do lots of things at the same time. And concurrency is important. In fact, have a die shot of a 32-core server CPU. That's a lot of cores, and using those can sometimes be difficult. It is about doing things while we're waiting for other things to finish, because sometimes you do something and it just takes some time. Maybe it's not on your computer. Maybe it's a long-running process that is just in the background. So, while we do that, we want to do other stuff, because it would be a waste to wait. We want to do all of this without race conditions. And I think Rust is pretty good at avoiding race conditions mostly. And there are some things you have to keep in mind. And Rust as a tooling system around the language prevents a lot of the errors that you will encounter. But so you could just use threads. And that's where the Async IO is different from most blocking IO, which means that it's about not using any threads. And how that works, we're going to go into in a second. So there's this picture from the Nginx documentation, or marketing material, I don't know actually, which sort of highlights, ignore that it says, Nginx is just an example here. It can be any asynchronous written software. And in a traditional server, if you have blocking I/O on multiple threads, each request will be assigned a thread from its beginning to its end, and then whenever it needs to do something, it will block. And then there can be a context switch to a different thread or something. But that also means that the thread that's now blocking to wait for something to happen is essentially wasting server resources. Now, obviously, your kernel can go and schedule that slightly differently, but you're still going to use some amount of resources and time when you switch between these threads. On the other hand, the Nginx worker, which is using an asynchronous threading model, will sort of make the request slot one after another and sort of make it all happen on a single thread without waiting. So far so good. Why would you want to do that? And that's a question that a lot of people sometimes don't know how to answer. There is a picture here that I want you to take with a little bit of a grain of salt. It's this graph, which maybe you know. It's from a Stack Overflow answer in 2012, so it's a little out of date. And also, I would urge you not to, yes, those are two server implementations. They are written in different languages and use different threading paradigms. They can't honestly be compared one-to-one. But I don't really want you to focus on what Apache is doing, or the blue graph. I want you to focus on what the red graph is doing, which is absolutely nothing. So the memory usage in an asynchronous threading model is usually pretty constant, or it grows very slowly, because the main overhead from using threads is memory and having to allocate a bunch of stuff and then swapping it around and switching out registers. And so if you have the capability and if you can do lots of things on the same thread while not waiting and sort of interleaving tasks, then that is going to save you a lot of memory, and it's going to make the usage of your resources a lot better. So maybe I have hypothetically sold you on the idea of using async programming. Doing this manually, like doing this manually, sounds like a bit of a nightmare. And yeah, it can be. And that's where sort of some asynchronous programming models come in, and we're going to go through them now and what they mean. And the cornerstone of all of this is futures. Not that type of futures, unfortunately, although it would be cool. No, a future is a calculation that hasn't yet happened. What that means is, let's say you want to read something from a different computer, so you send a network request, and now your network request is on the wire, and there's like stuff between, and the world is really big, and the speed of light is only so fast. And so you are talking about waiting for something to happen that is probably going to happen, but the probably here is important. It doesn't have to happen. And you're going to see in a bit why it doesn't potentially always have to happen, because, for example, a condition that requires, so a condition that is required for your future to run might never happen. You might never hear back. That is never going to happen. But it's probably going to happen, and you should just keep asking. Which, you know, this is a nice sort of abstraction over having to interleave lots of tasks yourself. You have an abstraction over a task. But it still kind of sounds like a nightmare to program for. And, well, that's why there's a second part to most asynchronous threading frameworks or systems, which is an event loop. An event loop is a runtime for your futures. What it does, realistically, is take ownership of a future and then run it when it is ready. And it keeps polling the future for it to be ready, and then when it is ready, then it runs some sort of code. And that really takes all of the work away from you and puts it into the work that needs to be done for the event loop. So yeah, this is a talk about Rust, apparently. So I want to show you what this looks like in Rust, or what it looked like in the beginning of the year. I hope you can see that. I had problems seeing code snippets all day, so maybe look at the TV. What this does is it reads from a reader into a buffer until it hits a new line, and then, when that is done, it writes something to standard out. And this might seem pretty simple, but this is a future, because you're asynchronously telling your program to read something, and then whenever that is at some point done, then it should do something else. And the and then combinator you see here is the actual future that is then added to this state machine. Realistically, this API allows you to build asynchronous state machines, where you sort of define what could possibly happen, and then you do it. And this is why a future doesn't always have to run, because imagine that instead of mapping the error to a panic, we then run a different future. It failed, oh, let's do this other thing. If it never fails, then that future is never going to get run. What's also important to note is this last line here. I don't know if I can't really select it in its entirety. The Tokyo run. Nothing up here, actually, like in the building the future, actually happens. It only happens once you give it to your event loop, and the event loop is then responsible for taking ownership of the future and then doing something with it. So that's what async programming looked like in the beginning of the year, and I kind of want to go back a little and talk about some history. So in an earlier talk, this was already mentioned, that Rust had a green threading model, and the year was 2013, or late, I think it was around December when it was added. And it was called libgreen, and it was one of two threading models that were present in Rust. One was a green threading model, and the other one was the libnative threading model. So you could choose between having green threads that enabled non-blocking async IO and having the sort of one thread per kernel thread approach. There was a common abstraction over both of them, and some people liked it. Talking to a few people who were involved in the language and the community back then, it's sort of unclear what everyone thought. It did have a few problems, though, one of which is that now you needed to include a runtime in libstd, because you needed something to actually run your features. If you have or you need some sort of abstraction over all of this asynchronous task scheduling. And this runtime was really heavy, and it also conflicted with something that Rust wanted to do. Rust wanted to go to different places. It aimed to be a more low-level language. Around the same time, like, Go existed, and nobody needed a second Go. So Rust became something slightly different, and it moved in a lot of ways. It became low-level, and as such, the runtime had to go. And only about a year later, in late 2014, libgreen was removed again, because no one wanted it. So yeah, November 2014, I don't have a timestamp for this next thing, but I think this was published in around December 2014, so someone took about a month to hack this together. This is a library that still exists and that's still being developed, and this is Mio, Metal IO. So what Mio is a light non-blocking IO library. In the same sense that libgreen used to be, it abstracts over several async primitives on different platforms and sort of enables you to use asynchronous threading models in your application. And it eventually also developed an ecosystem around it. There's adapters for different wire formats. So like if you want to talk to TCP, if you want to talk to a serial port, you can do this all non-blocking with Mio. And then for a while, nothing happened until mid-2016. And this is probably mostly because, you know, late 2014, in May of 2015, the language became stable, so there was lots of stuff to do, lots of things to clean up. And then after the language had become stable, the language wasn't really finished. It just meant that it had sort of a basic set of features that needed to be present. So it took another year after that to add features back in and sort of work on a lot of other stuff and get the ecosystem in a space where people could build better things with it. And so mid-2016, I think it was around June, this library came up. It didn't have that logo back then. It was just called Futures RS. I went for the meme over historical accuracy. So yeah, what was Futures RS? Well, Futures RS was a zero-cost abstraction for futures. Little show of hands, who actually knows what the term zero-cost abstraction means? Okay, that's half, roughly. So a zero-cost abstraction is an abstraction in code that you can use without that abstraction layer itself adding any overhead to your runtime. So for example, a really nice example is iterators. You can write a for loop or a while loop or whatever, and you can iterate over something in a loop and do something. Or you can take your collection, create an iterator, do a map and filter and fold or whatever, and then do something that way. And the iterator is not going to be any slower than if you write it as a loop. In fact, because the iterator takes ownership of your data and it gives the compiler a more linear path to reason about the mutability of your data, it can probably be a little faster as well, because the compiler can optimize more things. As with, you know, you have a mutable vector. You could do anything with that. Like the compiler can't reason about what's happening to that data. And in the same sense, like the iterator, there's zero cost abstraction over iterating over stuff. And so futures, the code that I showed you earlier, that uses futures, and that is a zero cost abstraction. You are able to write asynchronous state machines using an abstraction layer that at compile time basically disappeared, and it all just turned into functions. So it didn't slow you down in any way. And so the next thing that sort of came up on the horizon was Tokyo Core. It's just called Tokyo now, but back then it was called Tokyo Core. And I couldn't find the original logo. The current logo seems to have changed slightly. So what Tokyo did was wrap around MeORS, and which existed since 2014, and now wrapped around Futures RS, which just existed, so like a month or two later, and it added the event reactor part. It added the ability to take a future, run it, and not have to schedule everything yourself. And that was a huge game changer. And if we fast forward to 2018, like the code that I showed you, that's how people write asynchronous applications now. I've seen some in production. I've put some in production. So what's the problem? Well, let's look at that code again. It doesn't do a lot, does it? It reads from standard in into a buffer, and then it writes to standard out from the buffer. Yet the code actually looks quite complicated. So there are several nested things that are going on there, and we have a combinator that is and then. And it's rather difficult to actually reason about what this code does without reading it in its entirety, and you can't just look at it from a glance. And also, imagine if you want to do something slightly more complicated than just reading and writing from something, if you wanted to process something. So that was a bit of a problem. Really, what we would love to be able to do is write code like that. Something where you can look at it and go, oh, yeah, it reads into a buffer, and then it writes the buffer. And this is a lot easier to reason about than the other code. And this is exactly where Async Wait comes in. So what's the idea behind Async Wait? The idea is that you want to be able to write code that looks synchronous and looks blocking, but it actually does asynchronous stuff under the hood. Because this is a lot easier to reason about. This looks much nicer. You can look at it. It's 2 lines. So how does this work? Well, there's a few moving parts involved, and I'm going to walk you through what actually had to change for this to happen. And the cornerstone, I would say, of this is the future trait. So the future was introduced, I guess, by Futures RS, and people have been using that library specifically to write applications for a while. The difference now is that this is a trait which looks at futures a lot more generically. It looks slightly different. There's 2 parts involved in that. Can't actually see my mouse. There is a poll which has some type information attached to it, and it's either ready or it's pending, and you need to wait for it. And then the future trait itself uses an associative type called output, which then encodes the information of what you actually want to return as your future. The parameters for the poll function are like implementation specific. If you wanted to write an event loop, like if you want to write an event loop, you will have to understand what those are. But as a user of futures, you don't care, because your future is pollable, and well, sometimes it returns. And this is now in libcore. Like this code, removing the doc comments, is literally from libcore. And also there's some components of it in libstd, which add some utilities that are a bit too bloated to go into the core library. The second part to async await are 2 new keywords, async and await. You guessed it. So async marks a function as async, and await is sort of the opposite of that. It blocks on whatever you're doing and waits for it to actually finish and doesn't just run it in the background. And so if we imagine our function again that reads from standard in and prints to standard out, using async await, that's what it looks like. Let's say we have a function read and print, and it notice the async keyword in front of fn, which my syntax highlighter unfortunately doesn't really know about. And you return a result of a unit and an IO error. So you don't really want to return any data, but if something goes wrong, you want to tell the user about it. And then we have two await calls here. So we read until we hit a new line, which I forgot the single quote to close that. So we read until a new line, and we read into a buffer. And when that is done, we then write that buffer to standard out. And we wait on both of those calls. What that means is that this function can be called over and over and over again by your event loop, but inside the function, it is very blocking, because you can't really do a lot of concurrency on standard in and standard out. And so this code is basically the same as this complicated futures state machine, and it's a lot easier to reason with. The best thing about it is that async keyword, because what that does at compile time is change your function signature to that. So what the read and print function will return in the end is a future, or something that implements a future, where the associative type output is whatever you have. So like you see here, result unit stdio error, and then its output result unit stdio error. What that means is that you don't have to write that big cumbersome return signature every single time, and especially if you nest futures, you don't have to then go, well, output is a future of output is a future. So if you have nested calls to asynchronous functions, then it'll all be generated for you, and you really only have to care about the data that you actually want to return. So that's all nice and good. To use this, there was a bit of work done in the last few weeks, and this was, I think, announced and released just after RustFest, or like on the second Impl Day or something like that, and that is Romeo. Romeo is a very minimal Tokyo fork. It doesn't aim to replace Tokyo or even do everything that Tokyo does, because Tokyo does a lot of stuff. The thing that it did, though, is implement the async await syntax, and also the new futures API, so that you can now write asynchronous code in a runtime loop without having to worry about scheduling all your futures yourself while using async await syntax. So this in this example, we have a function called say hello, which I shortened to fit it on the slide, and we have a function called listen. Both of the functions are async. And one actually returns something and the other doesn't. And then when we listen on a port, and we've set up incoming connections. And then we have this while loop. And this while loop is really just a wait for a connection to come in and then reply something. And please also wait for the reply to be sent. But really, I didn't really have to tell you this, because the function itself is pretty clear. Right? So you await an incoming connection, and then you wait saying hello, and then you go into the next iteration of this sort of running asynchronously wherever it is possible. The beauty of this is now that Romeo will take care of the scheduling. So if you have multiple listeners or multiple things that can happen at the same time, if this becomes more complicated, like for example, you could have another future that sort of sends data into this listener, and it would all work because Romeo takes care of the scheduling. And you might be asking yourself, can I use this? It's a fair question, and yeah, you can, on nightly. So this is all very not stable. Let's look at what actually was done. And this brings us back into Rust 2018 and the things that had to happen for this to be a possibility. So there was an RFC for the async await syntax, which added the async await. You might have noticed that await is currently still a macro. That's because there's some further yak shaving to be done to the extent of where await should be applicable, how it should be scoped, and generally some of the finer implementation details. As I showed you, the future trait was added to libcore and libstd. And futures RS as a library updated to the new API using the futures trait instead of doing its own thing, and that is now in version 0.3 instead of version 0.1. Right. So I talked about community in the beginning a bunch, and some of you might be asking what the hell that was about. I want to talk about the networking working group a little, because the networking working group drove a lot of these changes. Now, it wasn't the group as a monolithic entity, obviously. It was people in the group who were active either in other parts of the community as well, in like certain teams, or it was people who were sort of drawn into the idea of helping write networking tools, who then started to contribute because there was a working group. And it turns out that writing networking code has a lot of problem domains, and that resulted in some tension and resulted in things like blocking each other and not moving forward as quickly as they could. And it really boiled down to the idea that there were 3 different camps of people. And there were the people who really just cared about the async await implementation, or mostly cared about the async await implementation, and that was important. There was people who just said, I want to write a web app, and I don't care. Like, I don't care if this is async. It should be async if it's faster, but like, I want a web framework that's like complete, and I don't have to do cookie handling myself, and please give me a database connector, and like that sort of networking framework where it's like, okay, sure, just do everything. And then also, like, Rust runs on embedded, and there's embedded chips and boards that have Ethernet or Wi-Fi, but they don't have an operating system. So what if I want to use async there? Because that would be really cool if I could write like a server on the one core that my device actually has, and I don't have to do any sort of blocking for I/O operations, and I can do everything asynchronously. That sounds pretty cool. And so what ended up happening is a bit of mitosis. Although that is, I think, defined as a cell splitting in 2 parts. Here it was 3. So we now have the net async working group, the net web working group, which is amazing to pronounce, and the net embedded working group to sort of aim exactly at these problem domains. And some of the people are involved in all 3 groups. It doesn't mean that the people are now at war with each other and never talk to each other again. It means that each of these problem domains has been given a platform to deal with things that come up, to sort of create a roadmap. Okay? And I think this is important to mention, that this wasn't a change that was made because someone decided that it would now be 3 groups. It was 3 different camps in the same group that sort of said, yeah, we have different priorities. We should split up and sort of make something that goes into 3 different directions. And I think this is the sign of a healthy community, where a group of people works on something and they can decide, you know what, this is the better path forward. So I want to recap a little. I talked about a bunch of stuff, and like, I promised there would be a point. A few days ago, 2 days ago, Aaron Turan published this blog post on the network working group blog, which is still a single blog. It hasn't mitosised yet. I don't know what the verb for that is. In this blog post, he actually describes a lot of the stuff that I've been talking about in this presentation, sometimes in more detail. So like, I told you to ignore the parameters that the poll function takes. There's like another whole trait involved. That blog post goes into it a little bit. So if you really care about the nitty-gritty implementation that I didn't think wouldn't fit into this presentation, go read that blog post. It's really, really interesting. It also goes into the things that haven't been done yet. And the talk description was about what has been done and what hasn't been achieved. And yeah, so what's still left? Primarily, futures aren't stable. So they're still a nightly, but that doesn't, they could theoretically be stable or stabilized. But like, their entire idea of what a future should even be and what the API should look like isn't stable yet. There's like an open RFC right now. People are asking for feedback and collaboration and contribution. And this is really why Romeo was forked from Tokyo, to give people a platform to actually experiment around with ideas, because no one wants to stabilize a trait and then in 6 months realize that it's really not the best way of doing it, and now everyone hates it. And like, well, it's unstable now, we can't remove it. So I think the thing that whenever I talk to networking people, they tell me is encouraging people to play with Romeo and like playing with Async Wait. Even if you don't write a production application that way, even if you just want to like hack something together and see what it feels like, and then giving feedback if you encounter any problems and you go, that doesn't seem right. And because now is still the time that feedback can be considered. In 6 months, it'll be too late. And the thing that then needs to follow suit is the ecosystem and the libraries, because just because Futures trait and core is stabilized doesn't mean that all your libraries are going to work. There's a whole ecosystem of things that use Futures 0.1 that should have to be ported to 0.3, and it's a lot of work that needs to be done. But I think so. Like, there's a community that starts building these things, and I asked myself this next question, when I was writing these slides. The talk title is an async story. And yeah, sure, I talked about async and I told you a story. But also, like, what the hell was my point with any of this? And I think that's a good question. So fundamentally, I think looking at the community, looking at Rust as a language and as a sort of collection of people, Rust is the async story. Like, who makes Rust? Rust in 2018, or async in Rust 2018, is still work in progress. But it's on a pretty good track. There's things that need to happen, but everyone sort of knows what needs to happen. We need some feedback. Code needs to be written. Code needs to be reviewed. But generally, it's getting there. And I think that is because it's not a small committee of people that are planning it, but it's a community. It's lots of people giving their feedback and talking about what they want, what they don't want, and how they want to get there, and making all the decisions that they need on the way there. If that includes splitting your working group up and focusing on smaller aspects and larger aspects and having different pictures and the same conversation, then so be it. Whatever it takes to get to the goal. Who makes Rust? Well, it's really easy. As I said, it's easy to consider a committee. It's easy to consider that the creators of this language are a bunch of wizards that sit in a tower all day and discuss the way that async should work in Rust in 2018. And then they come down and they announce their progress and everyone cheers and it's all amazing. No, that's not how it works. It's all of you. It's us. Like, we make the language. And the language is what it is today because of all of us and all of you. And I would argue that the language is better off because of it. So I talked about community. I talked about async development. I hope I made you at least curious about trying out Romeo, trying out this new futures concept, and looking into how you can write asynchronous networking code, because it really has a lot of benefits. But if I could ask you to remember a single thing from this talk, it's none of that. Well, part of that, but really none of that. It's fundamentally that collaboration takes time. Sometimes things don't work the way they were supposed to. Sometimes the first attempt sucks. And you have to deal with people. People are just the worst. People are the hardest problem in computer science. Everyone knows this. You have to await progress from the people that you work with. But when you do that, and when you pull together on the same rope, and you sort of collaborate in a way that it might not always be obvious to you from the start, then the result is going to be amazing. I know that async in Rust will be amazing because I see the conversations that go into making it. And I see the decisions that happen on a human level that go into making this technology. And ultimately, that, for me, is the async story of Rust. Thank you.